think about the air in the room that you're in. I'm in the Mass Center at Alamance Community College, and so in the room I'm in, there is actually, these large air ducts, air returns, and vents. And so at every point in this room, there's air motion. There's air actually moving. And so at every point in this room, I could assign a vector that both gives me the velocity, that gives me the velocity, the speed, and direction of the air motion. Every point in this room gets a vector, and that's what we call a vector field. A vector field is a vector function that assigns to every point in a domain a vector. And so I could assign every point in this room the airspeed and direction, right? The velocity of the air. Other examples we could think about, think about other velocity fields. We could think about velocity in a river, right? The actual motion of the river. At every point in the river, the water is moving at a certain velocity. We could think about gravity, right? Gravity is always pointing towards the center of the larger object. So I think about the gravitational field for the Earth. The direction is straight towards the center of the Earth, and we actually know an acceleration, which could then give us a force. Other force fields we could think about. We also earlier talked about special vectors for a curve, right? We talked about the vector big T and big N, the unit tangent vector and the principal unit normal vector. Well, if we take this curve to be the domain, well, for every point on this curve, T assigns a unit vector, and so that is a vector field. N also gives a vector field, and the binormal vector would as well. It would be straight out of the board here until I make that turn, and then it would be going below the board. All of those examples of vector functions. Notationally, if I had a three-dimensional vector function, it would need to take in an ordered triple and then give me out a vector based on those points. And so what I would see are three scalar component functions that give me the I, j, and k parts respectively. And so for us, vector functions are going to look like this. Vector fields are going to look like this, where every 3D vector field is going to have three scalar component functions. And this lets me define the idea of continuity. A vector field F is continuous if M, N, and P are continuous. So anywhere M, N, and P are all continuous, and F is continuous as well. So let's look at a few examples of vector fields, and we'll start with two vector fields that occur in the plane. And so what I want to think about first is the vector field given by f of xy is equal to xi plus yj. A pretty boring vector field. And I want to sketch this vector field, so I actually have a grid here, and I'm going to draw the vector field. Our convention is to draw the vectors at each point as if the tail of the vector was at that point. So let's first draw the vector at 0, 0. Well, that would just give me out the 0 vector, and I'll just plot a point there. And so now let's draw the vector that would occur at that point, 1, 0. And that would just be the vector I. So I draw the vector I, so it points one unit this way, but I draw it as if this was its base point. And so the vector I draw is actually there. All right, and so let's draw one more that's on the x-axis. So let's think about the vector that would be at the point 1, 2, and then 3, 0. And that would be the vector 3i. So I'm going to start right there, and then 3i points 3 units straight down the x-axis. So 1, 2, 3. All right, and now let's just think about what would happen if I did the same thing on the other side. Well, those x's just have the opposite sign, so not too hard to guess what would happen. Nice symmetry. All right, so there I have some very boring vectors. If I thought about going in the y direction, well, I'd have something similar happen. The I component would be 0, and I'd get the y coordinate out. So I'm just going to go on and draw those in. At any point, if you don't believe me, you can pause the video and just work through the details. All right, so I've drawn some vectors that would lie on the axes. So now let's take a more interesting point. Let's see what happens at the point 1, 1. Well, at 1, 1, I get I plus j. So I imagine starting at this point, and I go 1 unit in the I direction and 1 unit in the j direction. I end up right there. And if I stay on the line y equals x, well, I'm going to keep getting vectors that kind of point along that line. So 3 by 3. And then I think about it, right? X and Y are going to change signs as I go through the quadrants, and so I think I understand what will happen in each of those. And I'm picking points so that my vectors don't lie right on top of each other to make them easier to see. Every point in the plane would be assigned a vector by this process. So there's nothing really special about the ones I'm choosing other than the fact they're just the ones I happen to be choosing. And so looking at the vectors I've chosen to draw here, what I realize is that this is what I could call a radial field. If this was a velocity field, everything's moving away from the origin. If it was a vector field giving me a bunch of forces, everything's getting repelled from the origin. So that's a radial field. So let's see if we can do another example. This will be a more interesting example, I think. So this does two things. It swaps the x and the y that I plug in and makes this one have a negative value. And in both cases, I'm dividing by the square root of x squared plus y squared. Before I even get started, I'm going to do something different this time. I'm going to find the magnitude of this vector. In fact, pause the video and see if you have an instinct for what the magnitude of this vector will be for every x and y, and then see if you can compute it. Okay, so let's see. I need to square both components and add them together, so I'd end up with a y squared over x squared plus y squared plus an x squared over x squared plus y squared. I already have a common denominator, and I get x squared plus y squared over x squared plus y squared. This vector field is entirely comprised of unit vectors. So every vector I'm going to draw is going to have exactly the same length. So if I know if I know where a vector starts, I just draw a vector 1 unit long in the correct direction according to this vector. So let's start right here. The origin is not in my domain, right? I try to plug that in. So I'm not going to plot anything there, right? But let's start at the point 1, 0. All right, well, I know what happens for the I component, where I get 0 over 1, so I don't need to worry about that. And I just get 1 times j. All right, so now I think I actually understand what's going to happen for all the points on the positive x-axis. I get a j component and a y component, and they're all positive x's, 1 unit long. So on the x-axis, I just get a bunch of unit vectors that point straight up. Now I'm plotting these at the whole number values here on the x-axis, but that would be true for any place on the x-axis. If I hop over to the minus side of the x-axis, I'm going to have the same thing, except for the size difference. So instead of pointing up, they're all going to point downwards. And I feel like I'm committed to drawing all the arrows all the way out, but I think we understood it without me having to actually draw maybe that much. So I have a bunch of vectors drawn now. I'm wondering what's going to happen on the y-axis. So here I'm at the point 0, 1. The j component is going to drop off, but I'm going to get minus 1 over 1. I'm going to point towards the left. And in fact, for every point on the y-axis, all right, I don't think I'm going to draw all of the arrows all the way up here, but maybe that's enough. On the opposite side of the y-axis, now I have a positive going this way. All right, so I think I'm starting to understand what's going on in this vector field, but let's at least draw a few of the vectors kind of out here in the quadrants. So I don't know, let's start with 2, 2. All right, so I get minus 1 over root 2i plus 1 over root 2j, which definitely a unit vector, which is good because I needed a unit vector. And so starting at this point, I go to the left and then up in such a way that I end up with a vector that's 1 unit long, something that looks like that. And I realize that on the line y equals x, that's what I would always get. It's a vector pointing 1 unit that way. All right, moving over to quadrant number 2. Well, now both the I component and the j component will have signs that are negative. And so I start here and I go this way and down, so I get a vector pointing down. And so what I see is a vector field that appears to be spinning. And in fact, that's what's happening here. This is a spin field. It gives me a rotational spin. And you can actually plot more vectors in this field, but this is a spin field. And in the last example of a vector field I want to talk about, I actually want to talk about a 3-dimensional vector field. I want to talk about a gravitational field. So Newton's law of gravitation. Is about the force exerted by gravity. So what it says is if I have a mass, an object with mass m, and another object with mass m, then the force of gravity acting between them is given by this equation, where m and m are masses. And I usually like to think about little m being the mass of a little object and big M being the mass of a big object. But so far as this rule is concerned, it doesn't really matter. So if I think about myself, I would be little m. And if I think about the Earth, it would be big M. G is a constant. It's actually called the gravitational constant. And R is the distance between the two objects. And that should be a square, not a cube. Okay, so this gives me the magnitude of the force, right? And sometimes you might just see it written down without the vector notation there, but I want to actually write down what F equals, right? The actual vector field, the vector function that to every point would assign the force. So, what I want to do is imagine a situation. I want to imagine, so I'll make a note of Newton's law of gravitation here. I want to imagine an object with mass big M whose center is at the origin. So I'm actually, in my head, thinking about that as the Earth, and the center of the Earth would then be at the origin. So big M is the mass of an object whose center is the origin. Little m, I want to think about as the mass of an object at x, y, z, and I want to imagine now that I have a vector u that points to that point. So that's a position vector for the object with mass little m. Okay, so g is a gravitational constant, and then r is supposed to be the distance between them. Well, the center of the object with mass big M is the origin, and so r is actually equal to the magnitude of that vector u, the distance between that object or that object center and the center of the object with mass big M. And so I could think about the magnitude of u, which is just the square root of x squared plus y squared plus z squared. All right, so I can actually start putting things together in my notation now that I've identified where objects are and thinking about this position vector. So big F is then equal to m times g, but now over the magnitude of u squared, right? Replacing r with the notion of what u is. Well, vectors are two things, a magnitude, which I have, and a direction. And I know something else about gravity. I know that gravity is always pointing towards the center of the bigger object. So the direction of F should be u over its own magnitude, right? That's a unit vector. So now I know the vector's magnitude and I know its direction. I should be able to put that vector together. So F should be equal to, and I've made a mistake on the line before, and I've made this mistake before, and it's always silly. This direction is wrong, right? I want a vector that points from the object with little m towards the center of the earth, and so it wouldn't be this. That's pointing from the origin to my point. I need it to be the opposite of that. I need gravity to pull things towards the planet, not push them away. And every time I do this example, I make that mistake just for a moment, and it's always just a little bit funny that it's like I think gravity pushes things away. And you can pause the video here and laugh about that for a minute if you'd like. All right, so I have the vector's magnitude, and here is its direction. So, very technically, I've written down what the vector F is. I want to write it down in a little bit of a better way. So let's just rearrange things a little bit here. And here's where I had that u cubed snuck in there a little too early, right? I had that cube on that r earlier because I was already thinking about this moment, and I have u times u out here. So, and in fact, I know a little bit more about u, right? I know that u is the vector x, y, z. And I know the magnitude of u is the square root of x squared plus y squared plus z squared, which then I raised to the third power. So I could write that as x squared plus y squared plus z squared to the 3 halves. And so now finally, I can write down that vector field the way I like to see it written down. In the I direction, I just have all that stuff. In the Y direction, I have, in the J direction, I have now that distributed, so minus MMGY. And then finally in the K direction. And there is a vector field based on Newton's law of gravitation. So if you were to put in your mass and the Earth's mass, then this would be a vector field that would give the force of gravity for any point you were around the center of the Earth.